Now, I want us to understand something like this. Think about this before you answer the question. So we tell you, you are given a 1000/400 volt single phase transformer, right? Okay. And there's a question that says, calculate the secondary terminal voltage. Given a 300 kVA 1000/400 volt single phase transformer, right? So now I'm going back, and please, the N3 and the N4, please pay very careful attention. So if you look at the construction of a transformer essentially comprises of three parts. It has a primary winding, or one winding, and it has a secondary winding. Is that correct? Yes. Now, how does a transformer work? What is the function of a transformer? The function of a transformer is to step up or step down an alternating voltage with a corresponding decrease or increase with the current. That is the definition. So remember, the definition or the function of a transformer is to step up or step down alternating voltages with a corresponding decrease or increase in the current. Correct. So I want to explain to you very simply the operation, and please pay attention, this is coming from the N4. We start off by applying an alternating voltage V1 to the primary one. Right? Now I won't go into no load and full load, I'm just going to do the whole operation, assuming that this transformer is really working. This alternating voltage V1 is going to produce current I1. And when current I1 flows through the coil, what did we say this morning? It produces magnetic flux. It energizes or excites the primary coil. And that is going to produce magnetic flux. What type of magnetic flux? This is alternating. How do I know that? Because the supply is alternating. You see that? This alternating magnetic flux produced by the primary winding, it's looking for another winding. And what is it going to do? As soon as it finds it, it will induce an EMF. So this finds the secondary coil. And this is what Faraday said is mutual induction. Mutual induction means that we have deliberately created the alternating magnetic flux using which coil? The primary. And it is the magnetic flux produced by the primary coil that is now going to induce an EMF in the secondary. Is that correct? Is this EMF dynamically or statically induced? Statically. There's no physical motion. You see? But to be more specific, we say it is mutually induced. Mutually induced is one of the two types of statically induced. Now, students, I ask you this question here. This is 1000 volts. What is this? Can you see it's got nothing to do with the output? You see that? So therefore, when we gave you previously in N1 and in N2 and in all of the other textbooks, they said to us V1 was 1000. They said to us V2 was 400. That is not V2. Why not? That is the open circuit voltage. So how can we say that this terminal voltage is 400? It's not. That is why we asked you to calculate the terminal voltage for 7 months. So now, you are going to say, there's a formula which says V1 over V2 equals to N1 over N2. Right? And this V2, I have corrected it and said in that book, it's called V2 original. It was supposed to be E2, not V2. Do you agree? What did we say this morning is the function of the EMF? What does EMF do? It will wait. As soon as the circuit is complete, here's a complete circuit. What will it do? It will produce current. Which current? I2. Can you see? E2 produces I2. When current I2 flows through this impedance, depending on the type of load it's applied, R times Z, what does it equal to? Now it gives me Z2. You see that? So therefore, on the primary side of the transformer, how many quantities are measured in volts? On the primary side? One. Which one? V1.
Supply.
On the secondary side, how many quantities are measured in volts? Two. Which one? That's it. And what is the difference? The EMF is the open circuit voltage. And V2 is going to be influenced by the nature of the load. But what influences E2? Here you are going to say V2 original. What do I call it? I call it E2, open circuit voltage. E2 equals to V1 times N2 over N1. Now, when we talk about a step-up transformer, what does it mean? For a step up, the formula is telling you to make V1 bigger, what must N2 be? N2 must be bigger. So N2, the secondary terms, must be greater than the primary terms. If I want to create or build a step down, what must happen here? N2 must be less than N1. Please take note, colleagues, that the number of turns is influencing the open circuit voltage. It's got nothing to do with the secondary term. Now, the question arises, how am I then going to find that V2? How do I find it? There's a formula. Its derivation is there in the book, which says V2. Now, to avoid confusion, and I didn't want to tamper with the formula that's in all other textbooks, that is why I chose to call it V2 original, and I'm calling this V2 new. But what is actually V2 new? You see this part here? That is V2. That is the terminal voltage. That's what you're going to measure across the load. You on the output side. That's it. Right? So V2 new equals to V2 original multiplied by, what's the formula? 1 minus per unit rate. That is the reason why we taught you how to find the per unit rate. But remember, and I'm going to repeat this, the open circuit voltage is influenced by what? The number of secondary turns. Digest that. E2, or the open circuit voltage, is influenced by what? By the number of turns. Now what am I talking about? I'm not talking about E2, what am I talking about now? V2 new. Can you see that? V2 new has nothing to do with the number of turns. But what does it have to do with? The per unit regulation. And the formula says, there are three of them. One, if the load that is being supplied by the transformer is working at a lagging power factor, then the per unit rate equals to, give me the formula.
V2 new.
Is this correct? Right? Divided by, that if it's a lagging power.
Yes, yes.
Then the second one says, if the load, not the transformer can never work at a leading power factor, it's the load. But the question in the exam, they'll tell you a transformer works at a leading power factor. Right? So here we are saying for leading power factor, then the per unit rate is the same formula. And that is given to me by I times RE cos phi. What's the difference? Minus XE sine and divided by V. And the last one is when we tell you that the transformer is working at unity power factor. What's the formula? Per unit rate equals to I. You see, I'm learning now, eh?
You're doing well.
I'm sure you can change the color of your pen.
Yes, you can. Yes, you can.
divided by. Now what happened to the R, the XE sine phi? What happened to that?
Sine 0.
Remember it's cos phi, right? Cos phi equals to what?
1, sorry.
Equals to 1, right?
Unit, yes.
So cos phi equals to 1.
Yes.
Phi would equal to 0 degrees.
Yes.
Therefore, sine phi would equal to 0.
Yes.
Right? And you'll find here that the XE part goes
It's gone.
So now, for the 7 marks, can you see? What did you have to do? You have to work out the per unit regulation first, then substitute. Do you understand how a transformer works? So remember, the formula should have been V1 over E2. But it doesn't look correct. That is why I said, let's call it V2 original and V2. Does it make sense? Now the question becomes, can you see that this formula here has RE?
Yes.
RE, XE. It doesn't have R1 and R2. Why? Why?
The equivalent resistance after you refer other primary.
But why do we refer?
To make
Because the confusion that arises, and you are correct, the confusion that arises is in a formula you'll ask, do I use R1 or do I use R2? Remember, a transformer has 2 circuits, a primary and a secondary. So in order for us to simplify, we merge the windings. And after you merge, how many windings you have? 1. It's easy to work with. So you can bring the secondary winding and merge it with the primary. Or you can take the primary winding and you can merge it with the secondary. And that is where RE comes in from. So in order for us to calculate RE, XE, and Z, that brings us to the next part of the N6. How many methods are there? Don't tell me how to do it. How many methods can we use to find RE and XE? And ZE? Yes, very good. The first method is called
referring.
by referring. Now I'm not going to write down the formula, you know how to refer, isn't that so? So if you refer to the primary, you'll say resistance equivalent on the primary side. If you refer to the secondary, it's RE2. And you know the formula from here, isn't that so?
Yes.
What's the second method?
Using the short circuit.
Before that? Percentage or per unit method. Now, this one is very, very important. If I ask you to calculate voltage drop across a resistor, voltage drop across an inductor, what's the formula? I times R or I times XR. Is it then true to say that in order for me to find voltage drop, I need 2 things? I need current in amperes and I need something in ohms, whether it's resistance or inductive reactance. That's correct. When we look at this percentage there, I want you to impress upon the learners why the manufacturers of large transformers give us the percentage of a unit. If you take percentage Z, it's percentage R plus J percentage X. Correct? Dividing by 100 throughout. All you are doing is calculating per unit Z, which equals to per unit R plus J per unit X. Now, I tell you, I got a 10% increase. How much extra money did I have, or do I have now? I just told you 10%. But you don't know that, isn't it? So now, obviously, you can't calculate the round value because you don't know Raman. Is that correct? If you look at this, you cannot use percentage R or per unit X or per unit R in any of the formulas. Because to calculate voltage drop, I need current and I need ohms. Is that in ohms? No. To calculate copper losses, I need I squared R. R must be in ohms. Is that in ohms? So why do you think the manufacturer of a large 3 million rand transformer will give you useless information like this? Because I can't use it in any more formula. Why? There are two.
It doesn't matter what the actual value is. At the end of the day, it will decrease or increase by that percentage factor.
Yeah, but how do I convert it to ohms? Because I want it in ohms. That's my problem. Because remember, to work out voltage drop, it's amperes times ohms. To work out copper losses, it's ampere squared times ohms. Isn't that so? So why do you think? There are two reasons. The first one, and the book details it like this. First reason, second reason. There's a formula that says per unit R is I times R divided by V. Or per unit R is I times R divided by V. If you decided to refer to the primary, what does this become? What does this become? What does this become? If you decided to refer to the secondary, what does this become? But can you see the same per unit R? And that is correct. When it is a percentage, it doesn't matter of what value. It's 10% of that or 10% of that. Okay? So the first reason is it allows us to use 1% of per unit whether we refer to primary or to secondary. That's the first reason. Second reason, if I cross multiply here, per unit R multiplied by V1 equals to, finish that off?
I1 RE1.
So what will I get if I take amperes and multiply by resistance? Voltage drop. Can you see that? Without me knowing the current, I can still work out the voltage drop. How? You take the per unit R and you simply multiply by V1. Did I need the current? Yeah, there we are. Did we need the resistance? Did we need the current? Now, in M6 techniques, synchronous machines, we tell you the percentage impedance of the machine is. We don't give you the size of the alternator, and we ask you to calculate the volt drop. Can you see what formula you're going to use? Does it make sense? So, the questions that I want to come to. 400 volts is not the secondary terminal voltage. So, we will call it V2 new, and in order for us to calculate it, we use the formula V2 original, which is the open circuit, multiplied by 1 minus a unit. Correct? In that formula, we found that there was an RE and XE, and I'm saying to you, there are three methods that we use to find RE, XE, and ZE. What's the first method called? The method of referral. What's the second method called? The per unit resistance or percentage resistance or percentage impedance. Just remember, the reason why we give you percentage values, it can help you to find the voltage drop without even knowing the current and without knowing the resistance. What's the formula? Per unit R multiplied by V gives the voltage resistance. Per unit X multiplied by XL gives you the voltage drop due to reactance. Then there's the third method. What is the third method? Now, you said it at the beginning. What's the third method now?
Using the
This
test
is
results.
using the short circuit results. And when we use the short circuit, I want of you to draw a little circuit diagram, and I'm going to explain to you why. So here you are going to find that there is a voltage short circuit, and the second scenario is there is a voltage short circuit. Now, in the question, they're going to tell you that the short circuit test was conducted with the secondary winding short circuited. So go and short circuit this. Can you see with the short circuit? There's no voltage there. So you are going to say, this is VSC1. If we tell you in the question that the primary has been short-circuited, Then, can you see there's no VSC here? Instead, we are now short circuiting here. What are we applying? VSC. Do you understand that? Yes. So please tell the learners to draw the circuit diagram, because you need to know whether it is VSC1 or VSC2, and that influences the choice of your formula. Let me show you. Power on short circuit is I1 squared RE. You can also say our short circuit is I2 squared RE. Can you see? Which PSC? The same PSC. You don't need to change the PSC. Whether you measured it on the primary or secondary side, it doesn't matter. But here's the problem. VSC1 is I1 ZE1. Do you have VSC1? Do you have VSC1? Can you see what's given to you?
It's given, yes.
If the learner does this and says VSC is I2 ZE2, can the learner use the same VSC? No, because the function of a transformer is either to step up or to step down. Can you see? Now you must say here, this is VSC2. Did we give you VSC2 here?
No.
No. Now you need to work out VSC2. And you are going to say V1 over V2 is N1 over N2 equals to VSC1 over VSC2. You see where you get VSC2 from? So again, colleagues, when you are using the short circuit test to determine Z, please ask the learners to draw this little diagram. And they must work out which VSC is given. PSC is not a problem. Use the same PSC on both sides. But when we give you VSC1, to calculate VSC2, that's the formula. Do you think I've covered this here?